All right, so hopefully you're not waiting until Wednesday to watch this video. I'm hoping that you're watching it at home on Tuesday night. And the last video that we watched, wow, that was super long. But I put in a lot of notes and a lot of examples because it's such an easy topic. There's no reason you should miss it. So I gave you lots of notes. For lesson 10.2, it's prime factorization, and this is something that I think you did in elementary school. All my classes before have done it. One thing that we're reviewing is factors and factor pairs, and these are what is on the T-charts. So like right here for 24, they have some form of a T-chart, and I'm just going to turn it into a T-chart. And then the 24 would be up here. This is exactly like our factor flags that we have hanging around the room. So it says that Anna wants to build a rectangular garden with an area of 24 square feet. What are the possible whole number lengths and widths of the garden? So over here in your notes, you're going to write example 1, and you're going to draw all the ways you can make 24. You can have 1 by 24. That's one way her garden can look. You can have 2 by what? 2 times what is 24? 2 times 12. 3 times 4 also gives you 24. No. Erase that. We're doing 24. 3 times what? 8. Forgot we were doing 24. Okay, 3 by 8, and then we could also have a 4 by 6. I think I probably made that too big. Let me erase some of that. 4 by 6. I don't know. Something like that. 4 by 6. Really, the 6 side should be longer, right? Look how disproportionate I wrote. My side that's 3 is longer than the one with my 8. All right, but let's not have that. Let me delete that little piece. It won't let me delete it. Okay, well, so back over here, it says list all the factors of each number. So 21, we would have the T-chart for 21. Start out 1 times 21. 2 times anything? No. 3 times anything? Yeah. 3 times 7. 4 times nothing. 5 times nothing. 6, no. 7. It's already there. So it's 1, 3, 7, and 21. This picture that they have up here is the rainbow method, and a lot of you will see the rainbow method look more like this, more like a rainbow. 1 times 21 and 3 times 7. Okay, that's what they did here. They even put in pretty colors. Number 2, 37. 37. The only thing you can multiply to get 37 is 1 times 37. Okay, that's it. And we call that a prime number because there's nothing else that you can multiply to get 37. Okay, number 3, 42. 1 times 42. 2 times anything? Yeah, 42 is an even number, so 2 times what? What's half of 42? 21. 3 times anything? You're saying no, but if you take 4 plus 2, you get 6, and 6 is a multiple of 3, so 42 is a multiple of 3. I don't know what you multiply 3 by to get 42. That's why I'm going to divide it. All of this division and work needs to go in your spiral, in your notes. Okay, 3 times 14. because that's a 14 times 3, which gives you 42. 4 times anything? No. 4 times 10 is 40. 4 times 11 is 44. 42 is in the middle. 5? No, it doesn't end in a 5 or a 0. 6? Yes, that's a math fact. Plus, remember that rule, if it's even and divisible by 3, if it's divisible by 2 and 3, it will be divisible by 6. So yeah. And then that's it. 6 and 7 are consecutive when you count. They come right after, 7 comes right after 6, so that's the stopping point for that. So we have 1, 2, 3, 6, 7, 14, 21, and 42. All right, last one. Let's do 30. 1 times 30. 2? Yeah, 30 is an even number. Half of 30 is 15, so 2 times 15. 3 times 10. 4? No. 5? Yeah, it ends with a 0, so 5 will be there. 5 times 6. And look, there's that little clue again. If there's a 2 and a 3, then there will be a 6 also. And then 5 and 6 are right next door to each other when we count, so that's it. That's the stopping point for that. So our answer is 1, 2, 3, 5, 6, 10, and 15. We have this question here. Give an example of a whole number that has exactly 2 factors. Now, I'm going to be real picky. This is not a question, so there should not be a question mark here. It is a command. It's a command, so that should just be a period. Okay, what type of number has exactly 2 factors? So when you look at our factor flags, numbers that have 2 factors are these, and you can look at the factor flags to confirm it. 2 only has 2 factors. 3, 5, 7, 11, 13. They only have 2 factors, and those 2 factors is the number 1 and then itself. What do we call these numbers? Prime numbers. Okay? So I want to see this in your notes. This activity has us finding the prime factorization of a number. Prime factorization is one of our vocabulary words. So it says use a factor tree to find the prime factorization of 240. And they started us out here. Now, you know how to do factor trees from elementary school. I don't like the way they started that. I'm going to start with a different one. 240. If there's a 0 at the end, then that's going to end in 10. Or 10 is a factor. And then 10 times what? Everything that's before the 0. So 10 times 24. Neither one of these are prime numbers. So I keep going. 2 times 5. 2 is prime, so I'm going to circle it, and that stops there. 5 is prime. That stops. Okay, now 24. This factor tree should be in your notes. 3 times 8. 3 is a prime number. But 8 is composite, so I'm going to keep going. 2 times 4. 2 is prime. 4 is composite. So I keep going. 2 times 2. And 2 is prime. 2 is prime. And now we're going to write the prime factorization. And when we do this, we list the numbers in order from least to greatest. So as I write them down, I am going to mark them out. So there's 2 times 2. Hold on, this is not where I want to be writing it. Right here. 2 times 2 times 2 times 2 Okay, that's all the 2's. Now the next number would be 3 times 3. And then the last one is 5. So I had circled how many prime numbers here? 1, 2, 3, 4, 5, 6. And I have 1, 2, 3, 4, 5, 6 prime numbers in my prime factorization. Now the other part of D says write the prime factorization using exponents. Remember, the exponent tells us how many times that base is being used, or that factor. So 2 is being repeated how many times? 4 times. So that's going to be 2 to the 4th power. The little 4 goes up there. And then 3, there's only one 3, so we'll just write 1 3, and there's only one 5. Okay? That 4 didn't come out real super clear. Let me see if I can do it again. There. It's a little 4 up above. Okay, now, I didn't do this because this right here is going to save you time. The other thing is not. All right, so what if the factor tree, what will the factor tree for 240 look like if you start the tree with a different factor pair? So I'm going to do that real quick, and you can do this along with me in my notes. Did not mean to do that. And this time I'm going to start with 2. Anytime you take 2 times a number, the other factor is going to be just half of 240. So 2 times, well, half of 24 is 12, and then there's a 0. Okay, 2 is prime. I'm just going to go with 2 every time. 2 times, what's half of 120? 60. 2 is prime. What's half of 60? 30. So 2 times 30. 2 is prime. 2 times, what's half of 30? 15. Okay, this time I can't use 2. 2 is not a factor of 15. I'm going to use 3. 3 times what? 3 is prime. 3 times 5. Both of those are prime. So let's see, did we have 4 2's? 1, 2, 3, 4. Yeah. And then a 3 and a 5. Okay, so no matter how you begin, the prime factors are the same, period. This other method, I've heard it called ladder diagram, like they're showing you here, but also birthday cake. It ends up looking like an upside down, like wedding cake or layered cake. It's kind of like what I did with the factor trees, except it's like upside down division. Okay, we're going to do prime factorization of, let's do 240, like we did the other one, and we'll use the ladder method. Okay, 240, so it looks like this. 2, and then the other number was 120. The number on the outside over here has to be prime. Okay, and then let's make another layer of the cake around the 120 and use a prime number here. I'll just use 2 again. 2 times 60. Okay, can we use 2 again? Yeah, 2 times 30. Can we use 2 again? Yeah. 2 times 15. And then that's the end of the 2's, because 15 is odd. We can't use 2 anymore. Only use 2 on even numbers, so 3 will work. 3 times 5, and then 5 is prime. So it stops there. We don't draw a cake around the 5. Okay? And then these numbers on the outside is going to be your prime factorization. 2 times 2 times 2 times 2 times 3 times 5. 2 times 2 times 2 times 2 times 3 times 5. Okay, so this should go into your notes as well. We didn't do this example. We used 240 again. Complete a factor tree and ladder diagram to find the prime factorization of 54. Okay, so I know that 9 times 6 is 54. 9 is composite because 3 times 3 equals 9. And then that is, the 3 is prime, so that stops. And then for 6, 2 times 3, 2 is prime and 3 is prime. So that's the end of that. Okay, and then let's do the birthday cake method, the ladder diagram. I like birthday cake better. All right, 54, so I'm going to choose a prime number to begin. What I started with here, both of those numbers are composite. And I need to start with a prime number, so I'll just pick one of these, 3. 3 times what is 54? Honestly, I just don't know the answer to that, so I'm going to come over here and divide it. I don't know my 3's up to 54. Okay, so 3 times 18 is 54. So I'm going to put in 18 here. 18 is composite because I can multiply 3 and 6. 6 is composite because I can multiply 3 and 2. And then 2 is prime. So my prime factorization includes all these numbers. 2 times 3 times 3 times 3. Get the same thing. 2 times 3 times 3 times 3. So it's 2 times, and since 3 is repeating, I'm just going to write it one time. And how many 3's are there? There's 3 of them, so I'm going to put the little 3 there. Okay, so number 7 says if one person uses a ladder diagram and another uses a factor tree to write a prime factorization, will they get the same result? Yes, all numbers. No, wait. Let's see. How would we explain that? We would say 54 has the same prime factors no matter what. It's not a very mathematical explanation.